Greetings, calculus students. This lesson is on Newton's method. Now, the location of x-intercepts that are challenging to find or that represent irrational numbers can sometimes be approximated using a process known as Newton's method, illustrated below. So we have some sort of function intersecting the x-axis. This location is called an x-intercept, also sometimes called a root of the function. We'll use function notation. Now, the method is as follows. We begin with an x-coordinate that's near the root, and I'm going to call it x sub 1. We find the point on the function corresponding to this x-coordinate, and then calculate the tangent line, or the local linearization. Now, finding the root of a tangent line is easy to do, so the location of where this tangent line intersects the x-axis will become our next x-coordinate of interest. I'll call it x sub 2, and then we repeat the process. We find the point on the function corresponding to x equals x sub 2, find the tangent line, and then find the root or x-intercept of that tangent line. And we'll call that x sub 3. And then I continue. And in this case, we can begin to see that I've created a sequence of x-coordinates, x1, x2, x3, that appear to be getting closer to the location of the x-intercept of the function. Let me illustrate this with technology. So we have some sort of function. We pick an x-coordinate near the x-intercept, find the tangent line at that location, and then find where that tangent line intersects the x-axis, and then do this again. Find where this tangent line intersects the x-axis, and then repeat. Now I'm going to zoom in. Now the purple point you see here is the intercept of the blue tangent line. And I'll continue to zoom in. And now you can see that the blue tangent line is intersecting the x-axis very close to the actual x-intercept of the function. If I were to repeat this again, make a purple tangent line, zooming in, this orange point is the x-intercept of the purple tangent line. And I need to zoom in a lot to finally realize that it's not quite the same location as the x-intercept. But then I repeat again, and I make this new tangent line. Now we just keep getting closer and closer and closer to the actual x-intercept. This is known as an iterative process, meaning it's a process you just repeat over and over again until you've achieved the desired results. Now let's focus on just the first step. So we pick some x-coordinate, x sub 1. Then the y-coordinate would be f of x sub 1. So this orange point in our graph has coordinates x sub 1, comma, f of x sub 1. Furthermore, the slope of this orange tangent line can be found by plugging x sub 1 into the derivative of f. So m sub tan is f prime of x sub 1. Now let's create the equation of this tangent line. So you have y minus the y-coordinate is equal to the slope times x minus the x-coordinate. This would be the equation of that orange line. Now what we want to do is find the x-intercept of the orange line and call that x-intercept x sub 2, which means we want the y-coordinate to be 0, and then we're going to solve for x. So change y to 0 gives us this result. Now I'm going to divide both sides by f prime of x sub 1, assuming it's not 0. And then I'm going to add x1 to both sides, giving us x equals x1 minus f of x1 over f prime of x1. And this x that we just found would be our x sub 2. Then we just repeat this exact same process, but beginning with x2 as my initial. So in other words, find the green line and then find its x-intercept and call that x3. And doing so produces that x3 would be the exact same formula, x2 minus f of x2 over f prime of x2, etc. And so we can generalize this into the following formula over here, that to find x sub n plus 1, we look at the previous x sub n, and subtract the fraction f of x sub n over f prime of x sub n. And this formula applies for n values greater or equal to 1. So take this general formula and change all n's to 1, and you produce this specific formula. Take the general formula and change all n's to 2, and you produce this specific formula, etc. Now the formula will not work if x prime of x sub whatever is 0, then this denominator will be 0, and you cannot divide by 0. So the formula will fail. Visually, imagine we pick some x1 that takes us to a point on the function where the tangent line is horizontal. In other words, f prime of x1 is 0. Then that orange line will not have an x-intercept. So I will not be able to find x sub 2. And the process breaks. So our process will stop if ever f prime of whatever x will be 0. Okay, let's go to the next page. Consider the function below. So we have a function and its graph. Use Newton's method with x1 equals -1 to find x3 without technology. Okay, to use the formula, we need to know not only f, but its derivative. So calculating f prime, we get 3x squared minus 1. We are told to use that x1 will be -1. In our image, visually, what's going on is we're going to find this point and this tangent line, and then the x-intercept of that tangent line, and call that x sub 2, and then repeat the process. We don't need to find the equation of this tangent line and then find its x-intercept. We can now just use the formula. We know that x sub 2 will be equal to x sub 1 minus f of x1 over f prime of x1. So specifically, x sub 2 will be equal to -1 minus f of -1 over f prime of -1. So substituting in values, I'll do a lot of this work in my head, but looking at f, plug in -1 for all the x's. -1 cubed is -1 minus -1. So the first two terms will cancel, and then we'll get +1. So f of -1 is +1. And now let's plug -1 into f prime. So -1 squared is +1 times 3 is 3, and then -1 is 2. So in the end, we get that x sub 2 is equal to -1 minus a half, which is -2 halves minus a half, or -3 halves. So you can see there's slight error in my drawing by hand over here, because this location, as I've drawn it, doesn't appear to be exactly at -3 halves. But continuing by hand, let's find x sub 3 next. X sub 3, using the iterative formula, will be x sub 2 minus f of x sub 2 over f prime of x sub 2. Changing all the x2's to -3 halves. And now we have to do some evaluation. This will be a little bit harder to do in my head, so I'll show some more work. We have -3 halves minus. And now we have to plug -3 halves into the function f. So over here, every x gets changed to a -3 halves. Well, -3 halves cubed will be -27/8. Then we have minus -3 halves. That's +3 halves. And then we have +1 all over. And now we plug a -3 halves into f prime. -3 halves squared is +9/4. And then times 3 is 27/4. And then we'll have to subtract 1. So already you can see we have some tedious calculation now upon us. I'm going to take this complex fraction and multiply the top and bottom by 8/8. That's the least common denominator of all the subfractions. So 8 times -27/8 is -27. 8 times 3 halves, 2 divides in 8 4 times, and then times 3 gives me the 12. And of course, 8 times 1 gives me this 8. 8 times 27/4. 4 goes into 8 twice, so 2 times 27 is 54. And then 8 times -1 is -8. This numerator calculates to -7, and 54 minus 8 is 46. Then I need a common denominator, so multiply the first fraction by 23/23. So we get -69/46 plus 7/46, giving me -62/46, which we can reduce, these are both even, to -31/23. This was rather tedious arithmetic. We could continue to find x4 by hand, and the arithmetic gets even more complicated. So we're going to rely on technology to find subsequent values of x. In particular, let's use technology to continue until the root is approximated to 6 decimal places. So here in Desmos, I've typed in the function f of x equals x cubed minus x plus 1. Let's let x sub 1 be equal to -1. So type in an x and then a 1, and that becomes a subscript automatically, equals -1. Next line, we'll find x2 by using the formula x1 minus f of x1 divided by f prime of x1. It gives us a result of -1.5, which in fraction form is -3 halves, confirming our work. Now we can just type in the formula specific for x sub 3, or you can click this gear, hit this copy button, done, and then make some edits. Change this subscript to x3, and then the others to 2's, and we get -31/23, confirming what we did by hand. Now we're asked to continue this process until we have the root approximated to 6 decimal places. So I'm going to reveal the decimal forms of all of our answers. I want to continue the process until I no longer see changes to the first 6 decimal places. So copy, change to subscript 4, and change these subscripts to 3's. And between x3 and x4, I do see some changes to the decimals, so I continue. Copy, subscript 5, and these subscripts are all 4's. I still see some changes to the decimals between these two, so continue. And I'm starting to see some accuracy. The first 6 decimals here are 324,718, and here they are 324,717. But if I rounded using this 9, this would also be an 8. So we could say that our first 6 decimals are accurate once I do rounding. But let's do one more and calculate x sub 7 by using x sub 6 in the formula. And now I feel confident I have many decimals of accuracy. So in our notes here, we know the root was about this amount. I'm showing 7 decimals currently, and the 7th decimal is a 9, so we're going to round the 6th decimal up to 8, giving me these 6 decimals as a good approximation of this root. Now, of course, in Desmos, I can click on the function and then click on the root. However, the programming only shows us, in this case, up to 5 decimals of accuracy. So if you want more accuracy, Newton's process is a good way to achieve that precision. Okay, now visually predict what happens when x1 is equal to positive 1, and then confirm with technology. So if we use positive 1 as my first x-coordinate, and draw a tangent line, I'm predicting I'll get an x2 about this value. But when I go to the function and draw my new tangent line, it appears to take me to a location way over here, which is taking me away from the x-intercept. Right, back to technology, we have all the programming in place. I just have to change my x1 to positive 1. So our x2 will be 0.5, and then using 0.5, we calculate that our x3 is 3. So again, that went to the right as we predicted. x4 is 2, x5 is about 1.4, x6 is around 0.9, x7 is around 0.3. We don't seem to be getting closer to our actual x-intercept of negative 1.32. Showing the tangent lines, this is the first tangent line. The second tangent line, notice it does intersect at x equals 3. The third tangent line, fourth tangent line, fifth tangent line, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th. Ooh, finally I can see that the 13th tangent line, we were fortunate enough that it produces an x-intercept that's going to be on the left side of this peak, meaning I believe we will finally be able to hone in on the x-intercept. But clearly, choosing the first x-coordinate to be 1 was not beneficial, suggesting that we need to be strategic about what should be our initial value of x. All right, next page. Use Newton's method to find both x-intercepts for the function below, accurate to 5 decimal places each. For each x-intercept, calculate x2 by hand. Here's our function. I can see 2 x-intercepts. Let's focus on the one on the left first. It appears to be around 1/2. So I'm going to use 1/2 as my first initial guess. We have to be careful with this first choice because the natural log of x is only defined for x being positive. Notice we do have a vertical asymptote occurring on the y-axis here. So if you pick an x1, such as there, it could produce a tangent line that itself would have an x-intercept over here where the function's not defined, and that would be a problem. X equals 1 gives me a tangent line that when drawn by hand presents the risk of this occurring. So to avoid that risk, I'm just going to pick an x-coordinate where I'm confident the tangent line will not take me to x values that are negative. Okay, we'll need to know the derivative of this function. So f prime of x is 2x minus 2 minus 1 over x. So x sub 1, we'll use 1/2 to get started. And using Newton's method formula, we get x sub 2 will be x sub 1 minus f of x sub 1 over f prime of x sub 1. So we get 1/2 minus. Now we have to plug 1/2 into the original function. So 1/2 squared is 1/4 minus 2 times a half is 1. And then we have a minus natural log of a half over. And now we plug 1/2 into the derivative. 2 times a half is 1. And then minus 2, and then 1 over a half is 2. I won't be able to convert this entirely into a fraction because of the presence of this natural log expression. Well, 1/4 minus 1 is negative 3/4, and our denominator is negative 3. Let me move my work up a bit. Now I can divide both of these terms by this minus 3. So negative 3/4 divided by negative 3 is positive 1/4. Make sure to use some parentheses here because this negative will need to distribute. And then negative natural log 1/2 divided by negative 3 will go to positive 1/3 of natural log of a half. And then I can distribute this negative. And 1/2 minus 1/4 is 1/4. So my x2, I'll put in my table, is 1/4 minus 1/3 natural log of 1/2. This is what x2 would be in exact form, calculating it by hand. Typing this expression into Desmos, we get a decimal form of about 0.481049, rounded to 6 decimal places. Now we're going to use technology to iterate the process until the desired accuracy is achieved. So let's go back to this Desmos file, change my function, and notice that had I chosen x1 to be 1, it would have produced an x2 of 0. So the tangent line here would have had an x-intercept right here at 0, which is why the subsequent terms are undefined, because this function here is undefined for 0 or less because of the natural log of x. So instead, let's use 1/2 as my x1, confirming that x2 is about 0.481049. And then the process is already continued for us, and we're simply looking for 5 decimals of accuracy, which actually occurred rather quickly. Looking more than 5 decimals, I can see that we have consistency between x5 and x4, 5 decimals would be 0.48140, which I see actually occurred here at x3. And even if I do rounding, the 6th decimal is a 0 here, meaning that rounded to the 5 decimals, that our root is approximately 0.48140. And we got that accuracy with x3. So we've followed these instructions by indicating which iteration first achieved the desired accuracy for this x-intercept. Now let's focus on the second x-intercept. I can see that if we let x sub 1, our initial guess, be a 2, I'm imagining a tangent line that'll take me to a new location that is closer to the intercept, and then from there, I'm imagining another tangent line that will get me even closer. So I think 2, being x sub 1, is a good first initial guess. So our x sub 2, which we'll calculate by hand, will be 2 minus f of 2 over f prime of 2. So we get 2 minus, now we calculate f of 2, so plug 2 into the f function. That'll give us 4 minus 4, which is 0, minus natural log of 2. So just a simple negative natural log of 2. And now plug 2 into the derivative. Right here, we'll get 4 minus 2 is 2, and then minus a half, and that's 3 halves. So an expression that's a little bit easier to simplify, we get 2 plus, dividing by 3 halves is the same as multiplying by 2/3, and then natural log of 2. I'll put that in my table. Typing this into Desmos, we get about 2.462098 for my x sub 2. And now let's go to my Desmos file where the function's already typed in. I just need now to change x sub 1 to 2. And I'm looking for stability in the first 5 or 6 decimals. I see changes between x4 and x5, but between x5 and x6, I see the same first 6 decimals, 363,938 and 363,938. So in either case, when I round to 5 decimals, I would get 36394. So my x-intercept is approximately 2.36394, and this occurred by the time we got to x sub 5. Okay, let's go to the next page. Note that the square root of 2 is an irrational number that cannot be expressed as a fraction of whole numbers. We will use Newton's method to approximate square root of 2. Okay, you'll notice that we don't really have a function presented to us. What we want to do is come up with a function that has a root of radical 2. So we want our root to be square root of 2. If I square both sides, that would mean x squared needs to be 2. And then if I subtract the 2 over to get a 0 on one side, this sort of reveals to me a good choice of a function whose root is square root of 2. So this will be the function that we use with Newton's method. Because I know that if I find the roots, I would set the function equal to 0 and solve for x this way, and I find square root of 2 as a root. But how big is the square root of 2? What is a good decimal approximation for it? Are there fractions that we can find that are close to the square root of 2? That's where Newton's method will become helpful. Of course, we'll need to know the derivative. So the derivative of this function is 2x. And we're told to let x1 be the greatest integer less than square root of 2. So in this case, we want to find 2 consecutive whole numbers between which we find the square root of 2. Well, the square root of 2 will be less than the square root of, if you increase the radicand, then I know the square roots will preserve that same relationship. In other words, because 2 is less than 3, then square root of 2 will be less than square root of 3. Now 3 is not a great choice because it doesn't simplify to a whole number. So think of a radicand that's bigger than 2, but for which the square root produces a whole result, and that is the square root of 4. Do the same thing going less than 2. 1 comes to mind because the square root of 1 is a whole number. So this tells me that the square root of 2 will be somewhere between 1 and 2. And we're instructed to let x1 be the smaller of these 2 consecutive whole numbers. In other words, 1 is the greatest integer that's still less than the square root of 2. Okay, using Newton's formula, x1 will be equal to 1. Therefore, x2 will be equal to x sub 1 minus f of x sub 1 all over f prime of x sub 1. So in this case, 1 minus f of 1 over f prime of 1. F of 1 is found by plugging 1 into this function. Will give us 1 squared minus 2, or negative 1. F prime of 1, plug 1 into this derivative function, and we get 2. So we get 1 minus negative a half, or 1 plus a half, which is 3 halves. And per instructions, we're expected to find x3 without technology. x3 will be x2 minus f of x2 divided by f prime of x2. So we'll plug 3 halves in for all of these x's. So x3 is 3 halves minus f of 3 halves, plug 3 halves into this. 3 halves squared is 9 fourths minus 2. Well, 2 is 8 fourths, so 9 fourths minus 8 fourths is 1 fourth. And now f prime of 3 halves, and we get 2 times 3 halves is just 3. Now a fourth divided by 3 is a 12th. So you have 3 halves minus a 12th, get a common denominator, so 18 twelfths minus 1 12th, and we get 17 twelfths. And now we are to use technology to find a fraction of whole numbers that matches the value of square root of 2 up to 6 decimals. So back to our Desmos file, change the function to x squared minus 2. We can see the root that we're looking for is about 1.41421. This shows us 5 decimals of accuracy. We also know that that root represents the square root of 2. Change my x1 to 1. So x2 is 1.5 in fraction forms, 3 halves, confirming our work. x3 is this decimal that you see here, convert to fraction, is 17/12, confirming our work. And now I want to scan ahead until we see 6 decimals of accuracy. Between x3 and x4, I see changes in those decimals. Between x4 and x5, I see changes in the 6th spot, because there's a 5 here, and here the 6th spot has a 3. Between 5 and 6, I see no change to any of the decimals I see. So I feel confident that x sub 5 gives us the accuracy that we want, and Desmos is still giving us a fraction option. So our 5th x in this process in fraction form is 665,857 divided by 470,832. This is a fraction of whole numbers that is approximately the same as the square root of 2, accurate up to 6 decimals, which is about 1.41421, and then the 6th decimal will round from 3 to 4, because the 7th decimal is a 5. In fact, in our technology, if I just type in square root of 2, notice here it's showing me many decimals of precision, and you can see all the decimals here match all the decimals you see for x7, for x6, and even for x5. Now notice that for x6 and x7, you do not see options to convert to fractions. That is because the fraction calculations get so complicated that Desmos is switching over to decimal approximations with high accuracy. But certainly, in theory, all of the approximations in this case could be written as fractions of 2 whole numbers. Okay, let's go to the next page. Newton's method can present challenges in cases where there is a vertical tangent or near vertical tangent at the x-intercept. Use technology to complete the table and ponder your findings. So we have a rather unusual function, the cube root of x minus 1 plus 1/10 of the arctangent of x. There's clearly an x-intercept here. It appears to be near 1. I'm not sure if it's at 1 or just close to 1, but at this location, the tangent line does appear to be nearly vertical. Now we're told to go up to x10 for all of these initial x-coordinates. Currently, I've only written up to x7, so I'm going to copy the formula 3 more times to make up to x10. Just so I can see x10 near x1, I'll bring it up higher. So now my x10 is near my x1. Okay, new function, the cube root of x minus 1. I'll do cube root by using a 1/3 power plus 1/10 of the arctangent of x. We can see the function. Let me zoom in a little bit. You can see the x-intercept isn't quite 1. Okay, let's begin with an x1 of 0.7. Then x10 is about 108.47. I'll just round to 2 decimals and put that in my table. Look at the sequence of x's that led to that. Here's my x2, my x3, my x4, my x5, my x6, x7, x8, x9. There does not seem to be any sort of stabilization occurring. Let's change x1 to 0.8. This gives me ultimately an x10 of about 68.44, which I'll put in my table. 0.9 as my first x-coordinate leads to a 10th x-coordinate of about 28.43. Now we saw that the actual x-intercept is about 1, and if I plug in 1 for my initial value, notice I get right away for x2 even, undefined. And all of these therefore are undefined. Now why is that? We'll look at our notes. Let's find the derivative of this function. Let me first rewrite f of x using a power instead of a cube root. So we have x minus 1 to the 1/3 plus 1/10 arctangent of x. So the derivative, using the generalized power rule, the 1/3 drops down, the base stays the same. The new power is -2/3. Chain rule is times a 1 plus 1/10, and derivative of arctangent is 1 over 1 plus x squared. Well, another way to write this derivative, that negative power pushes this x minus 1 to the denominator, and the 2/3 power is the cube root of x minus 1 squared. So you can see the formula is going to fail when you try to do f prime of 1, because when you plug 1 into this part of the derivative, you'll get a 0, but in the denominator. So f prime of 1 does not exist. So we can't even get to x10 because f prime of 1, right away, we have failure to be able to use the formula. All right, back to technology, plug in 1.1. We get an x10 of about -39.03. Plug in 1.2, we get about -85.47. 1.3 gives us about -141.66. So you can see it's challenging. We knew that the x-intercept was near 1, but all of these x1 choices that are near 1 or including 1 lead to results that don't seem to be helpful. I'm going to use technology and tangent line visuals to show how 0.7 ultimately turned into 108.47. So here's a graph of our function. We picked 0.7 as our first x-coordinate, made a tangent line. It led to a second x-coordinate of 1.4502 approximately. Then the next tangent line produces an x3 of about 0.01091. And then just continuing this, focusing on the x-intercepts of each new tangent line. So here's our next number in the sequence. Next tangent line, way over here, negative. Next tangent line, I have to zoom out, way over here and positive. Next tangent line, zoom out, way over here, negative. And you can see this problem is just going to compound. So this is a good example of a function for which Newton's method presents some challenges. However, if you begin with an x-coordinate very close to 1, 0.999, we do see stabilization occur. And by the time we get to x10, we have a pretty close approximation of this x-intercept. But I had to use an x1 that was already fairly close to the actual x-intercept. Put this data in our notes. All right, and this concludes our lesson on Newton's method.